So I hope you can see my slides. Welcome to my talk on optimization of teams with neural networks, dynamic design of workflow, and training. My presentation is structured as follows. After an introduction and motivation, I will present the theory. The model uses recurrent neural networks to integrate differential equations describing, for example, time-dependent and interdependent variables of a given application. As an example, I will show selective results on production and personal planning. The model allows, in particular, the estimation of parameters required to obtain a specific particular goal in the output quantities. The talk then concludes with a summary and an outlook. So optimization of a workflow and task completion are relevant objectives in teams of companies or in general organizational structures. Team building and learning in teams, on the other hand, are important mechanisms affecting employee satisfaction and gain of experience. So personal planning to find somehow a compromise in these opposing goals plays an important role. It is important to develop methods that allow estimation of system parameters in a way to guarantee required effectivity, but also allowing passing on experience within the team, even though this may cost time. The challenge, so, is that we have competing effects, as very often in differential equations. So increasing the experience within teams and increasing efficiency may be opposing goals. One may thus have to find a compromise depending on, for example, personal structure or long-term personal development, as well as depending on boundary conditions such as schedules or quality standards. As this is a problem in many applications, our example is somehow representative for many other dynamic systems. It was inspired by cooperations with industrial partners. The time dependence of such objectives can be described using differential equations. And neural networks are very capable of learning the dynamics given by such a set of differential equations. They are particularly well suited for solving them, even in cases where traditional methods may be computationally expensive or difficult to apply. Furthermore, they allow easy adjusting and estimation of parameters that can be chosen in order to obtain a specific output behavior in the curve. In our model, we implement such a direct integration of ordinary differential equations through recurrent neural networks using Python. So the figure visualizes the implementation of a fourth-order Runge-Kutta integration scheme. The model allows for both inclusion of real experimental data as well as data generated with differential equations based on known or estimated dependencies that are included via a set of parameters. The neural network can then learn system behavior by training with various constant datasets. It is then afterwards tested with time-dependent data. If dynamics can be locally approximated by such equations AZ plus BU, linear, it is then afterwards easy to find solutions. The neural network finds solutions faster and works more efficient compared to a network learning only by using input-output data without an approximation equation structure. In our example of production and personal planning, the controlling parameter is the proportion of people working in a team. It's called here T. So the competing targets are as follows. Efficiency mu is larger when experienced person work alone. and smaller when they spend time explaining processes in a team with unexperienced person groups, affecting the overall productivity, here Z1, as can be seen in the equation. However, the gain of overall experience, Z2, increases if teamwork is applied due to the transfer of knowledge. The normalized number of teams is here denoted with T, and typical applications are, for example, pair programming. The set of equations for the total efficiency Z1 and growth in experience Z2 thus include dependencies on, for example, number of experienced and unexperienced person, the number of teams used in personal planning, and the effectivity of individual person groups and the overall group. In addition, the overall efficiency rises with factor E if there is more experience in the group in a later time step because there's now more experience. Application to any targeted curve of the time evolution of efficiency and experience as test data enables conclusions about the optimum team constitution following these curves. That is, the fraction of persons working alone or in a team to get as close as possible to the targeted values of the overall efficiency and experience. The advantage with this model structure based on differential equation is that you can rearrange it. So by rearranging the equations in the matrix form, time dependencies can be flexibly shifted and integrated in either matrix element in the algorithm or the control value U as in this previous slide. So a time dependence in the generated test data is applied in various factors, either in the efficiency in general, this is here model 1, the average number of experienced and unexperienced person in a team, here model 2, or the efficiency of the persons working in a team, model 3. As an example, we here use periodic variations in the test data, but of course any other dependency works the same. It is important to realize that for the training, only constant data was used, either artificially generated with the differential equation or just by real data. So these figures visualize the predictions, efficiency in blue and experience in green, independence on time when applied to test data here in gray with some fluctuations applied with different parameter sets and time dependencies according to model 1, first row, so the efficiency variation, and model 2, second row person variations. So the prediction of the neural network allowed in each case for an estimation of a suitable team fraction T required to produce the respective wanted output curves. So the first figure refers to a team factor of 0.125 and moderate left and stronger right modulations in the output quantities. And due to the low team factor, the values here of the experience in these normalized quantities are low. For the same person structure, the second figure visualizes that an increase in team fraction is correlated, of course, to higher values for the gain in experience in green. So the next two slides show the same situation, but this time for a higher percentage of experienced person for a low team factor, and then in the next slide, a higher team factor. And now the green curve representing experience shows larger values due to the higher percentage of experienced persons. Again, although the training data was generated without time dependence, so with constant values, the simulation clearly showed that a system could be trained to reproduce the modulation and the modulated test data for variable temporal periodicity, omega, and to estimate factor T appropriately. We would like to know that any other factor can be estimated the same way. It's just here an example of this team fraction due to this collaboration. The next slide confirms this, simulating a time dependence efficiency of people working a team using the third model. So the periodicity and the efficiency of people working a team for lower average values in UT in the first row and larger values in the second row. So the team fraction increases from left to right. So we can see an increase in UT, of course, leads to an increase in the overall efficiency. And it's the blue curve. And from left to right, we can see that an increase in the experience in the group can be reached and controlled with an increase in T as expected. So you can steer and control the output depending on how many people you put in a team. And in all cases, the trained model was suitable to predict given taste data and to see which parameter estimation is here required. All three models allow confirmation of test curves and estimation of suitable team factors. The collection shows once more examples of model 1 left and model 2 in the middle column and model 3 on the right for estimation of team factors rising in the estimation from top to bottom. So generally, we can use the model using large parameters regimes for all parameters. We can mix them all up. And for example, we can also use a parameter matrix for various experience levels of the working people. We can also include person-dependent working hours, as well as a set of different tasks requiring maybe different workload and time. All these time dependencies can be included, and this has been done and will be done again. The model then estimates a chosen parameter to reach best this given output curve for the overall efficiency and experience with time. Furthermore, the modeling also works for completely freely drawn curves, not generated with any model and variable parameter set based on equation, but just freely drawn. Just curves that approximately show dependencies fitting to the equation structure and principle. The model then finds a best fit and parameter estimation. To conclude, the integration of differential equation solvers into neural network architectures enables the construction of hybrid models that combine data-driven learning with physically based system representation of coupled systems, differential equations. Neural networks are suitable for predicting the outcome of systems with uncertainties and to estimate parameters appropriately, as in our case for production planning and similarly in other dynamic systems. The modeling is very modular and can be efficiently transformed to similar other systems that are based on differential equations. This is the end of the talk, and I would like to thank you very much for your attention.